Okay, today we are starting a new chapter, chapter 5 in your textbook, and that is adsorption. I hope you are studying. There is a lot of material that accumulated. I'm sorry that we are going through this in this fashion, but we have to do the best we can. So, adsorption, I'll go slow. I think this chapter will take 2 lectures. Today's lecture will be shorter, and the next chapter, the next lecture, we will finish this chapter. So, again, please study. Adsorption. Remember, whenever we say add, we talk about a surface phenomenon, something that takes place on a surface. Absorption with B instead of D. Okay, that's something that absorbs something. Plants absorb their nutrients from soil solution. Adsorption can be defined as the accumulation of a substance or material at an interface between the solid surface and the bathing solution. Sorry. So we have the soil solids, and mostly here we talk about generally the soil colloids. They are bathed, soaked in the soil solution, because you cannot have any type of adsorption, or most of the reaction that takes place in the soil system, they have to be in wet soil where you have soil solution. So adsorption can be defined as the accumulation of a substance or material. We will see what kind of substances or materials we talk about in this case. At an interface. The interface is the face between 2 phases. We have the solid and we have the soil solution. So the interface is that area between the 2. It's considered part of the soil solution, and also at the same time it's part of the solid that is soaked in soil solution. Adsorption can include the removal of solute molecules from the solution and the attachment of the solute molecules to the surface. So if we have molecules or ions in the soil solution, and if we say they are adsorbed on the soil colloids, so it includes the removal of the solute molecules from the soil solution, so they left the soil solution and they got attached to the solute molecules, to the surfaces of the colloids of the soil. Adsorption does not include surface precipitation or polymerization processes. So if compounds precipitate on the surfaces of colloids of soil clay minerals or the humus, that is not adsorption. It does not, and it should not include precipitation or polymerization. That's when we talk about organic compounds. Adsorption, surface precipitation, and polymerization are all examples of sorption. Remember here we are very specific. We're saying adsorption, the surface phenomena of a specific thing. We'll go into details of this process as we go on. If we say sorption, we did not specify adsorption. Sorption, that is a general term. It can include adsorption, precipitation, polymerization are all examples of sorption. So don't mix up between adsorption and sorption. A general term used when the retention mechanism at the surface is unknown. If we know it's adsorption, that's very specific. It's a process, we know what it is. If we don't know if it's a mixture of adsorption, precipitation, polymerization, or we don't really know the mechanism, what's happening on that surface, then we say sorption. There are various sorption mechanisms involving both physical and chemical processes that could occur at the soil mineral surfaces. So what holds these molecules or ions or whatever materials are adsorbed on the surfaces? They have different mechanism, sorption mechanism or adsorption mechanism in our case, involving both physical and chemical processes. Again, we'll go through that a little later. It's important to remember certain terms that are used in this process. They're specific and you should differentiate between them. They're easy, but be careful not to mix one term with another. It's useful to define a number of terms pertaining to retention, adsorption, sorption of ions and molecules in soils. The first of these terms is the adsorbate. Adsorbate is the material that accumulates at an interface. So it is the molecule, the material that accumulated at that interface. The solid surface on which the adsorbate accumulates is referred to as the adsorbent. So adsorbate, adsorbent. Adsorbent is the soil colloids, whether organic, inorganic, it could be a clay mineral surface, whatever. That is the material that adsorbs, where the adsorption takes place on its surface. The adsorbent is the solid surface. The molecule or ion in solution that has the potential of being adsorbed is the adsorptive. Some of the molecules or ions already been adsorbed, so they became adsorbate. If they are in solution still, but they can be adsorbed later, we call them adsorptive. They have the potential. That means they can accumulate on the surface. They can leave the salt solution and go to the surface and be adsorbed on the surface. So as long as they are still in solution, but capable of being adsorbed, we say they are the adsorptive. If the general term sorption is used, if we don't know exactly that what's happening is adsorption, but rather the general term, which we just said ago, if we don't know the mechanism, then the material that the material that accumulates at the surface, the solid surface, and the molecule or ion in solution that can be sorbed are referred to as sorbate. Instead of adsorbate, we say sorbate. Instead of adsorbent, we say sorbent. Same, remove just the AD, like sorption, adsorption. So just remove the AD and they are the same words. And sorptive, instead of adsorptive, we say sorptive. That is when we don't know the real mechanism. We don't know that what's happening is only adsorption. What's the importance of adsorption in soils? Adsorption is one of the most important chemical processes in soils. It determines the quantity of plant nutrients, metals, pesticides, and other organic chemicals returned on soil surfaces. So anything that's on the surface of colloids is adsorbed. So it can be plant nutrients, metals, heavy metals, pesticides. Pesticides, remember, so many different pesticides, including insecticides. Don't mix pesticides from pests, which includes all types of chemicals that can be used as herbicides, insecticides, rodenticides. We saw them in the first chapter, if you remember, we talked about those. And organic chemicals also that can be retained on the soil surfaces. So it determines the quantity of all of these that can be kept in the soil system on the surfaces of the colloids. Therefore, it's one of the primary processes that affect transport of nutrients and contaminants in soils. Remember, If they are held on the surfaces, that will reduce their mobility. They will not be moving easily and going down to the underground water, leaching through the soil. So that surface or the surface of the colloid holding those. So therefore, it's one of the primary processes that affect transport within the soil system, movement of nutrients and contaminants in soil. Adsorption, sorry. Adsorption also affects the electrostatic properties. Example, coagulation, settling, the settling of I don't know if you probably will go through some of this or already have in soil physics when we talk about settling of the colloids, the silicate clays, the clay colloidal system, settling if certain nutrients, certain ions will allow them to disperse, and some other will allow them to coagulate and get larger particles and settle down to the bottom of the suspended particles. If you remember, go back to your soil physics and see how sodium, say, will allow the particles, the clay particles, to stay suspended. But if you exchange the sodium with magnesium or calcium, there will be coagulation of the smaller particles together to form larger particles, and they settle down to the bottom of your vessel, whether it's cylinder or beaker or whatever they are in. Both physical and chemical forces are involved in adsorption of solutes from solution. Remember a while ago we said physical and chemical processes because they can be physical and chemical forces that hold these adsorbates to the surfaces of the adsorbents. Physical forces include van der Waals forces and electrostatic outer sphere complexes. Remember, we already talked about outer sphere and inner sphere complexes. If you have not studied the soil solution, remember chapter, you go back and review. We will go over this again, but these terms you should already know. Chemical forces resulting from short-range interaction include inner sphere complexation that involves a ligand exchange mechanism, covalent bonding, and hydrogen bonding. So the physical forces, simple, not very strong. Van der Waals forces and electrostatic outer sphere complexes. Remember, when we talked about the outer sphere and the inner sphere, we said the outer sphere always weaker because there are water molecules separating the ion or the entity that's adsorbed from the colloid surface. The inner sphere, there is no water molecules separating them, so they'll be closer, it'll be stronger. So the chemical forces result from short-range interaction, closer, that include the inner sphere complexation that involves a ligand exchange mechanism, so we can have exchange reactions, covalent bonding, covalent, remember, you know about sharing electrons, and hydrogen bonding. Hydrogen bonding, we talked about it also, if you remember, in the fundamental clay structures when we talked about the hydrogen bonding holding crystal units together. Okay, now what keeps some adsorbate to be adsorbed on a surface, on an adsorbent? There are what we call the functional groups that are important. They are on the surface. Surface functional groups in soils play a significant role in adsorption process. Remember, we talked about functional groups when we studied the soil organic matter. So there are also inorganic functional groups. We can have functional groups on the surfaces of the organic or inorganic colloids. A surface functional group is a chemically reactive molecular unit. A surface functional group is a chemically reactive molecular unit bound into the structure of a solid at its periphery such that the reactive components of the unit can be bathed by a fluid. It's simple. I mean, it sounds complicated, but we'll go over it again and explain it simply. So a surface functional group is a chemically reactive. It has to be very reactive. That means it can react. It can go into a reaction. So it's a reactive entity. Molecular unit bound into the structure of a solid. So it has to be bound, part of a solid structure, part of a soil colloid. It has to be part of it. But where is it? At its periphery on the edge. It cannot be hidden inside, and we call it functional group. It has to be on the surface, on the outside of it. So at its periphery, the outside part of it, such that, so what will happen? Because it is on the surface, the reactive components of the unit can be bathed by a fluid. Remember, sorry, when we talked about the first one, we defined adsorption, and we said they have to be some solid material bathed in solution. The solution we're interested in is the salt solution. That's what the fluid we're interested in our case. The fluid is the salt solution. So these reactive components of the unit that are part of a structure, that means part of a colloid, whether organic or inorganic, silicate, clay minerals, humus, whatever, and that functional group is on its surface. So it can be bathed, it can be soaked in and covered by the fluid, in this case, salt solution. That's when it's important. That's when we can call it a surface functional group. Surface functional groups can be organic. Example, we already, like I said, we talked about that in the soil organic matter chapter, carboxyl, carbonyl, phenolic, and many others, or inorganic molecular units, which we will talk about a little later. The major inorganic surface functional groups in soils are the siloxane surface group associated with a plane of oxygen atoms bound to the silica tetrahedral layer of phyllosilicates. You remember? We already studied the phyllosilicates, and we knew they were tetrahedral sheets and octahedral sheets. The silica tetrahedral layer, okay, if it is attached to it, then we call it siloxane. So the major inorganic surface functional groups in soils are the siloxane surface groups associated with what? With the oxygen atoms, which are bound to the silica tetrahedral. That's where the siloxane, remember, Si from silicon, siloxane. That's part of the silica tetrahedral layer of the phyllosilicate. And hydroxyl groups associated with the edges of inorganic minerals such as kaolinite, amorphous materials, and metal oxides, oxyhydroxides, and hydroxides. Remember, we all call them the oxides, but when we want to talk about each one specific, we differentiate between the oxides, oxyhydroxide, and hydroxide. All of them, if you remember, if you studied well, collectively, we call them the oxides in the soil system. Okay, we'll talk more about, because they are extremely important in adsorption, the surface functional groups. The surface functional groups can be protonated or deprotonated by adsorption of hydrogen and hydroxide or hydroxyl ions. If you remember, I have already told you in soil system, when you talk about protonation, that means the attachment of a hydrogen. Deprotonation, that is the loss of a hydrogen. So they can be protonated, they take a hydrogen, or deprotonated, they lose a hydrogen by adsorption of hydrogen and hydroxyl ions. Let's take an example. Again, S, it can be any surface. Remember, this is part of a surface, and these are functional groups attached to it. So S That's the surface. Okay, so OH, now it got protonated, so it took the hydrogen and it became OH2 plus. Now it has a positive charge. If it deprotonate, it loses the hydrogen, so it becomes SO negative. S is not sulfur, don't mix. You remember it's written this way to indicate the surface this functional group is attached to. So if it loses the hydrogen, it lost it to the solution, and now it has a negative charge. In chemistry, we're not going to go, in details. You already should have this. They talk about Lewis acids and bases. The Lewis acids are denoted, expressed by, or we write how we express them, how we tell about them by S. So this expression S is denoted by, that means we express it and we say it's this way. And the deprotonated surface hydroxides are Lewis bases. The Lewis acid sites are present not only on metal oxides such as on the edges of gibbsite or goethite. Gibbsite is AlOH3, goethite FeOOH, if you remember, but also on the edges of clay minerals such as kaolinite. So they can be in any of those. Most of the time, it's very hard to find them on the 2-to-1 surfaces, 2-to-1 silicate clay mineral surfaces, but the oxides, all the metal oxides and hydroxides, and on the 1-to-1 type clay minerals like kaolinite, you find these functional groups. Okay, there are also singly coordinated OH groups on the edges of clay minerals. We talked about the edges again, remember, I have discussed it for you earlier. When we take a soil clay mineral particle or crystal, it has to end at one point. And when it ends, how it ends, because it's made of so many crystal units attached together. These cannot go forever. At some point, it has to break, stop. Okay, so that will be an edge where it was broken, ended. On the edges, we can have OH groups exposed. Remember, these functional groups have to be on the periphery, on the edges, it cannot be embedded inside, and we call it functional groups. It has to be on the surface. It has to be able to be bathed in salt solution, so it will be reactive, and we can call it a functional group. Okay. At the edge of the octahedral sheet, OH groups are singly coordinated to Al3+, and at the edge of the tetrahedral sheet, they are singly coordinated to silicon. So they're loose, they're on the edge, but still they tied up to either aluminum or silicon, depending on we are talking about the tetrahedral or octahedral sheet. The OH groups coordinated to silicon dissociate only protons. So they dissociate only they give you protons. However, the OH coordinated to L dissociate and bind protons. They take protons. Dissociate and bind, but two. Dissociate and bind, that means they can do both. But for the silicon, they dissociate only protons. They do not associate, they do not bind protons. These edge OH groups are called silanol, SiOH, and aluminol, AlOH, respectively. Again, it's very easy to remember. Silanol from Si, silicon, that means it's related to the silicon, SiOH. Aluminol from the beginning, aluminum, aluminol, AlOH, respectively. That means silanol to silicon, aluminol to AlOH. That's what means respectively, as they in the same order they are given. Okay, now we talk about the complexation, how the complexation takes place, the adsorption takes place. When the interaction of a surface functional group with an ion or molecule present in the salt solution creates a stable molecular entity. It's called a surface complex. We will go over it again. When the interaction of a surface functional group, remember, we already know what's a surface functional group, what are the requirements of that functional group, so that we call it a surface functional group, with an ion or molecule present in the salt solution. So we have either ion or a molecule in the salt solution. It's gonna go to the surface to interact with the surface functional group. Remember, that's what adsorption is. It has to be removed or leave the salt solution, go to the interface. And at the interface, there is that functional group, which is bathed in salt solution. So we have this ion or molecule, which is present in the salt solution. It interacts with the surface functional group. And what does it create? What is the result of that? It creates a stable molecular entity, which we call surface complex. The process is complexation, and what happened, what was created, is the surface complex, which is made of the functional group and that ion or molecule that got attached to it. The overall reaction is referred to as surface complexation. Complexation is the process. Complex is what has been formed. The form is, think of it as like molecule, think of it as whatever you want to call it, but that's the complex between functional group and the ion or molecule. Okay, the process itself, the reaction itself that created this complex is the complexation. Okay, there are two types of surface complexes that can form: outer sphere and inner sphere. We talked about them again earlier, but that's what it means. If a water molecule is present between the surface functional group and the bound ion or molecule, the surface complex is termed outer sphere. We already talked about it. I'm not going to go into too much detail again and again, because we have already defined that in salt solution, and here we've been talking about it again also. So review back again your chapter and keep up with what we already discussed. If there is not a water molecule present between the ion or molecule and the surface functional group to which it's bound, this is an inner sphere complex, closer, no water molecule separating them. It is an inner sphere. Look at figure 5.5, page 143 on your textbook. It shows you their nice drawings. I'm sorry, I didn't have those in the lecture, but you can look at them closely and investigate them, and it's easy. If you really read what's written there and look at them close, look at them, not just quick look like that. Look at these figures, study them well, and I'm sure you will understand what we are talking about. Inner sphere complexes can be monodentale, metal is bound to only one oxygen, and bidentate, metal is bonded to two oxygen, and mononuclear and binuclear. Again, this is the best thing is to look at this figure 5.6 in your textbook, and it has very nice drawing, and it differentiates between all of them. It shows you the difference between monodentale, bonded to only mono bonded to only one oxygen, bidentate, the metal is bonded to two oxygen, and mononuclear and binuclear. Okay, the same with having one element or two element. Nuclear is where the nucleus is. Outer sphere complexes involve electrostatic coulombic interactions and are thus weak compared to inner sphere complexes in which the binding is covalent or ionic. So we have already talked about earlier that the outer sphere complexes are weak. And why they are weak? Because they involve, what are the forces that hold them together? electrostatic coulombic interactions between positive negative. These are simple charge attraction, okay, and are thus weak compared to the inner sphere complexes, in which the binding, what binds these, what holds them together, covalent or ionic bonding, which is very strong. Outer sphere complexation is usually a rapid process because there is no water molecules separating it quickly. So because there is water, because there is water molecule between the two, it's very quick, no strong interaction. Remember, electrostatic coulombic interaction is weak and it's reversible. That's why it doesn't hold very strong. It can go reversible very quickly. And adsorption occurs only on surfaces of opposite charge to the adsorbate. Because if you talk about electrostatic coulombic interaction, that's the attraction between positive and negative charges. So they have to be of opposite charge. You cannot have positive attached to a positive or negative attached to a negative. They have to be of opposite charges, one positive, one negative. The inner sphere complexation is usually slower than outer sphere complexation because it involves covalent or ionic bonding. There are bonds that forms. Okay, it's often not reversible because it's not easy to reverse when you have this type of interaction, bonding. And it can increase, reduce, neutralize, or reverse the charge on the sorptive regardless of the original charge. So remember, sorptive is what's in solution and capable of being adsorbed. So no matter what their charges is, due to this type of covalent or ionic bonding, the charge, it can increase the charge of that sorptive, it can reduce its charges or neutralize it, or change make it the opposite, reverse the charge on the sorptive, regardless of what it was its original charge. Adsorption of ions via inner sphere complexation can occur on a surface regardless of the surface charge. Remember, because of the type of bonds that takes place, it doesn't make any difference what is the surface charge. It's important to remember that outer and inner sphere complexation can and often do occur simultaneously. What does that mean? It doesn't mean that on the same site you can have outer sphere and inner sphere. No, that means on the same colloid you can have some sites that are having outer sphere and other site inner sphere complexation. So simultaneously, that means at the same time, but not at the same site. So that means in different places, different positions on the colloid surface, you can have outer sphere and inner sphere complexation happening at the same time. Ionic strength I, we already know what's ionic strength, we studied it and we saw how we calculate it. Effects, remember, effects, noun, the effects of something on something. If you want to say something affects something, the verb affects with A. So ionic strength effects, تأثيرات, the effect of it on sorption are often used as indirect evidence for whether an outer sphere or inner sphere complex forms. So if we study what does the ionic strength, the increase of ions in the solution or the decrease of it, that's what it means when you talk about this ionic strength, remember. What are the effects on the sorption? We can, from that, decide, do we really have an outer sphere or inner sphere? Indirectly, indirect evidence, so it gives us an evidence, but not direct one, indirect. So it's like a proof in an indirect way. How? The lack of ionic strength effect on sorption would suggest formation of an inner sphere complex. So when we change the ionic strength, when we change the concentration of ions around the complex that where the sorption is happening, and it did not change it, the lack of, that means no effect of ionic strength on the sorption process, then that indicates it's an inner sphere complexation. If it depends on it, the strong dependence of sorption on ionic strength, if changing the ionic strength changes the complexation process, that suggests an outer sphere complexation. So we finished this lecture. Next lecture, we will try to finish the chapter.